Using the thermal resistance equation that we previously derived in a different video, we can use that to determine the thermal resistance of a pipe with insulation surrounding it. Imagining that problem, we have a pipe of radius R1, and around it is an insulation of radius R2. Taking this equation that we derive for thermal resistance, we have that our change in temperature is equal to our heat flow multiplied by natural log of our resistance 2 over resistance 1 divided by our negative thermal conductivity multiplied by 2 pi height. So as we know, this is analogous to an electrical circuit. Our voltage is equivalent to our change in temperature, our current is equivalent to our heat flow because they both flow, and our resistance is equivalent to this entire expression right here. Now this is the thermal resistance for conduction. And we need to also know the thermal resistance for convection because those are both occurring within this problem, right? You have your air flowing on the outside and you have this insulator that's keeping the air more out, so the temperature doesn't change as much. So for our thermal resistance for convection, we know that our heat flow via convection is equivalent to our heat flow coefficient multiplied by an area multiplied by a change in temperature. Using our analogy for conductivity and our electrical circuit, we know that this change in voltage is equivalent to this change in temperature, and that this current is equivalent to this heat flow. So rearranging the equation, we can find what our thermal resistance for convection is. And that is going to be our change in temperature is equal to our heat flow multiplied by 1 over our height, our coefficient, sorry, not our height, multiplied by our area. So for this problem, I am going to change height from H to L. So it's easier to understand the difference between a coefficient and the length. So now we know that 1 over our thermal coefficient multiplied by our area is the thermal resistance for convection. In an electrical circuit, the total resistance is equivalent to adding each resistance in the circuit together. And so that concept we're going to use for this problem, if we want to find the total thermal resistance for this problem between the pipe and with the pipe and the insulator, we need to add the thermal resistance for the convection and the thermal resistance for the conduction. So our total is equal to R of convection plus R resistance of conduction, and that is equal to our convection is 1 over our coefficient multiplied by our area, which is 2 pi r2. That's where our convection is occurring, multiplied by the length, not the height, the length, because we're not using our height, we're not using h this time. And added to that, we have our longer equation, which is natural log of our second radius over our first radius divided by negative thermal conductivity multiplied by 2 pi L. Taking the derivative of this equation with respect to the second radius, we find that the derivative for our total resistance with respect to our second radius is equal to 1 over our coefficient multiplied by 2 pi L times negative 1 over r squared 2. Then added to this, we have 1 over our thermal conductivity coefficient multiplied by 2 pi length times r1, radius 1 over radius 2 times 1 over radius 1. So canceling out some of these terms, our r1, we get that the derivative of r total over with respect to our second radius is equal to 1 over our coefficient multiplied by 2 pi L R squared 2, this is all negative, plus 1 over our thermal coefficient, thermal conductivity multiplied by 2 pi L R second R. And we know that this derivative is equal to 0. So we can rearrange this equation and get that 1 over thermal conductivity multiplied by 2 pi length radius 2 is equal to 1 over coefficient 2 pi length radius 2 squared. Cancel out that to get a final equation of 1 over thermal conductivity 2 pi length equals 1 over thermal coefficient 2 pi length r squared. Continuing on, canceling out certain variables, we find that our second radius is equal to our thermal conductivity divided by our thermal heat coefficient. And so if we plug this back in to our derivative for total resistance with respect to our second radius, we get that 1 over thermal conductivity multiplied by second radius minus 1 over thermal heat coefficient multiplied by our second radius squared. Now let's find the second derivative. So the second derivative of our total divided by our second derivative of our radius is equal to -1 over our thermal conductivity multiplied by our second radius squared plus 2 over our thermal heat coefficient multiplied by our second radius cubed. So now we can take our R2 that we calculated out and plug it to this expression, and that will help us determine when our radius for our insulator is too large or too small, and it becomes not reasonable anymore to keep adding insulation, or there's not enough insulation. Plugging that in, we get an equation that says this plus 2 over, there we go, cubed. Canceling out certain terms, we get our thermal heat coefficient squared over our thermal conductivity. And because our second derivative is positive, we know that the graph is going to be concave up, right? We took our second derivative with respect to our second radius, and we found h squared over k cubed, and that's positive, so our graph is going to be concave up. Graphing this out, we'll say that this line is our total. And somewhere on this line, the very beginning, we have our base pipe, and that's a pipe without any insulation. That's going to be 1 over our thermal heat coefficient multiplied by the area, 2 pi r2 times the length. And as we add the insulation, we're going to get to a point where our radius is equal to our thermal conductivity divided by our thermal heat coefficient. And it's going to create a concave down graph, as we discovered. Eventually, it will start to increase. But what we can gather through this graph is that as we add the insulation, there's going to be a point in which the insulation actually decreases how it keeps heat in or keeps heat out, right? So it's actually going to be less efficient if we add that insulation. But then eventually we'll get to a point where we're adding enough insulation to where it's helping. So you just have to find this critical point that shows the perfect amount of insulation to perfectly insulate the pipe. So now we have discovered the total thermal resistance for a pipe with insulation, determined the second derivative for that total resistance with respect to R2, and then determine why there is a minimum number for R2, right? And clearly, as R2 increases, there's a point in the graph that tells us that we're not adding enough insulation to where it's actually decreasing the effectiveness of the pipe. And then there's a critical point which shows us exactly where the insulation is perfectly working and it's very ideal, and that's what you're looking for in a real world scenario.